Hey boys and girls, today we're going to go through and talk about the electron arrangement of an atom. If you remember last presentation, we went through and talked about isotopes and ions, and hopefully remember that an ion occurs when you happen to gain or lose electrons. Well, a nice sequential point would be, let's talk about all of the electrons in general. How are they basically organized around the nucleus itself in the electron cloud? So today we're going to talk about how the level works, or how the energy works. And basically, different energy levels are dictated by how far or how near the electron is to the nucleus. Basically, the closer you are, the lower your energy level is. And subsequently, the farther away you are from the nucleus, the higher the energy. Okay? So basically, when we think about this, each electron will have a different energy state based on its proximity to the nucleus. The further away you get, or the more space between the nucleus and the electron itself, the more energy that electron will have if it happens to be gained or lost in a bonding process. Okay? And each individual level has a maximum number of electrons it can hold. And when we look at that, basically the first level can hold 2 electrons. Your second level can hold 8 electrons, your third level can hold 18 electrons, and your fourth level can hold 32 electrons. We're actually going to look, for the honors kids a little later, how these second, third, and fourth levels break down into suborbitals, or sub-energy levels, but that's a future problem for future us. And you'll never have to worry about going past the fourth orbital in this class, but if you happen to go past it, there are, again, limitations to the number of electrons that can hit those energy levels. So, another major point we need to think about is that electrons must occupy the lowest energy level first. Okay? And basically it's kind of like thinking about if I was going to put a bunch of marbles into a cup. I can't put a marble halfway up a cup and expect it to stay there. It's going to fall to the bottom. It will fill the bottom level with marbles, and then as soon as the bottom level is full, if I continue adding marbles, they will stack further and further on top and layer themselves. I can't have an electron, in a similar fashion, occupying a middle energy level, so like the third level, if there are openings in the second and first level where it could fall into. So electrons will always occupy the first level first, the second level second, and it will fill up those levels before it moves on to a subsequent level. In terms of kind of trying to help you visualize this stuff, we're going to look at the idea of Bohr diagrams. And Bohr diagrams basically just show the different energy levels of the atom. So they are going to show every single electron that happens to be around an atom. So helium, knowing that we've got an atomic number of 2, should have 2 electrons. And those 2 electrons are found in one single level. Lithium, however, having 3 electrons, happens to have 1 and 2 on the first energy level, and it will have its third bumped out to the second energy level. So it'll have 2 on the inner level and 1 on the outer, giving it 3 total. Okay? So again, being that they're organized into different shells and levels, you can only fit 2 electrons on the first level, and once you get a third electron, that third electron is kicked to the second energy level. And then your second energy level will continue to fill up until it has 8 electrons. And once you get a 9th electron, well, I hate to say 9th, an 11th electron, 2 from the first level, and then the second level fills up with 8. Once you get to 11, that 11th is going to get kicked to the third energy level, and so on and so forth. Okay? So what we need to do is take a little practice here. See if you can go through and figure out the Bohr diagrams for these following atoms. So go ahead and give it a pause and see what you can come up with. So taking a stab at hydrogen, we'll go through and we know that we've only got 1 electron, so there's going to be 1 energy level, and there's your 1 electron. Looking at boron, we know it happens to have 5 electrons, so I'm going to have 2 of them on the inner ring, and then I'm going to go through and I will have 3 on the outer ring, giving me 5 total. If we happen to work our way down to fluorine, we know that it happens to have 9 electrons in a neutral state. So again, I'm going to have 1 and 2 on the inner, and being that I've got 7 left to go, that's not going to completely fill up the second ring, so I know that all 7 are going to fit on that outside ring. 1, 2, 3, 4, 5, 6, 7. Okay, so that gives us 9. And silicon's where we start to get really fun. Silicon actually has 14 electrons, so I'm going to have 2 on the inner ring. I'm going to have 8 on the second shell. Okay, that's 4, that's 5, that's 6, that's 7, and that's 8. And almost just as a double checking, I'm going to kind of have a little fun here. We've got 2 here, we've got 8 here. That means that if I'm going to get to my full 14, I need to have 4 more on the third shell. 1, 2, 3, and 4. Okay, so hopefully that makes a little bit of sense. We'll practice that a little bit more in class, but the visualization of this will kind of help us out when we start talking bonding within the next unit. Okay, and it does kind of help with the idea of valence electrons a little bit too. A valence electron is basically going to be your outermost shell of electrons. Okay, and they determine the properties of the element, specifically what other elements the specific atom will bond with, how reactive they're going to be, and all of the reactivity kind of ideas there. Okay, so in this case right here, we know that we happen to have 6 protons and 6 neutrons, meaning that this is an atom of carbon. This carbon itself has 2 electrons on its inner shell, and it's got 4 electrons on its outer shell. So we got 1, 2, and then the outer has 1, 2, 3, 4. So if I were to ask you how many valence electrons it has, valence electrons are 4. I'm not worried about the inner shell, solely the outermost shell. How many electrons are in that? Okay. And the valence electrons, and we'll talk about this a little bit, are the only electrons that are ever going to be involved within bonding. Okay, and we'll talk about that a little more next unit. And you can go through and you can actually do some counting for all that, or you can kind of realize that the periodic table tells you everything, and with the exception of our transition metals, so this set right here, there's not specific numbers for. But if you look at everything else, our first family here happens to have 1 valence electron. And it's set up that way that everything, hydrogen, lithium, sodium, potassium, rubidium, all happen to have 1 valence electron. If we work our way down to the beryllium family, or not beryllium family, your alkaline earth metals, these guys happen to have 2 valence electrons. And your boron family happens to have 3 valence electrons. And your carbon family happens to have 4 valence electrons. Nitrogen's at 5, oxygen's at 6, your halogens are at 7, and your noble gases are at 8. Okay? And it's because they're all set up so that they have the same number of free electrons in their valence shell. Okay? So you can go through and you can walk through a long process like we did last set with all of this counting out, or you can go through and just kind of look at the periodic table because it tells you how many are in each one. There is one giant exception to this, however, and our one giant exception is helium. Helium does not have 8. Okay? Helium actually only has 2 valence electrons, and that's because helium only has 2 electrons. Okay, but the reason that we call it a noble gas, and the reason that it's over here in this column, is that remember how many electrons can fill in on the outside of that first shell? You can only have 1 and 2. So any more electrons around helium would create another orbital or another shell, and because that means this first level is full, it has the same properties as the other noble gases over here. And we'll worry about that later when we talk periodic table. Okay. So again, go ahead and give this a pause, bust out your periodic table, and see if you can figure out how many valence electrons each of these atoms has. No, but seriously, pause it and try it out. Do it. Alright, so sodium, being over in our alkaline metals, happens to have 1 valence electron. Boron happens to have 3 valence electrons. Chlorine happens to have 7 valence electrons, and neon happens to have 8 valence electrons. Okay, and if you didn't like my writing, boom, computer says what's up. That was a little lame. And really we could go through and kind of look at how this is going to relate with an idea of Lewis dot diagrams. Basically, Lewis dot diagrams are our second form of diagram. Remember, our Bohr diagrams basically showed every single electron in ring form. Lewis dot doesn't worry about that. Lewis dot diagrams only show valence electrons. Okay, so the only thing I care about when I'm drawing a Lewis dot diagram is valence electrons. Okay, so in this case, our first group, lithium, you're only drawing 1 dot. Our second group, you're drawing 2 dots. Our third group, you're going to go ahead and draw 3 dots. So you're basically indicating how many valence electrons are around each individual atom. Okay? So when we go through and look at this stuff, there are a couple of rules that are applied to this. Number one, first thing you're going to do is you're going to write out the symbol. So in this case, we're going to take, let's say, phosphorus as an example. P. Write out the symbol. Figure out how many valence electrons it has. So I know looking at phosphorus, it's in the nitrogen family, so it should have 5 valence electrons. Okay, 5 valence electrons. Well, third thing we can do is I've got to set up so that it's 1 dot or 1 electron on each side. And each side can only hold 2 maximum electrons. So you can only have 2 dots per side, but each side must get 1 before any side can get 2. So what I do is I start off at noon. I go noon, 3, 6, 9, and back to noon. Okay, so that ends up with my 5 valence electrons. So setting them up so that they are at your north, south, east, west, or the 12, 3, 6, 9 works for either case, but that would be what I would use to kind of format these Lewis dot diagrams. And so again, the maximum number you can have is 8 because you can't have more than 8 valence electrons on the outer shell. Okay. So go ahead and I'd say take a second, try it out, but we'll try out a couple of those in class, and hopefully that'll be pretty quick and simple and make some sense. Anyways, honors kids, we'll go through and we'll set up a second video for the actual suborbitals themselves. They'll be your honors edition. For the CP kids, that's about all we got. We'll do it again some other time.